Hello everyone. Today I'm going to have a talk on something related to syntactic sugar. The paper's name of our work is the lazy desugaring system for evaluating programs with sugars. Let's start with the high-level motivation. Nowadays, programming is becoming more and more common, especially out of traditional programming field. Actually, we shouldn't expect everyone to learn the general programming. For example, considering we have a machine of making drinks, sometimes new products are to be added in the menu, where different operations of the machine are needed. In such case, domain-specific language will be easier to use. If we want to make different domain-specific language, syntactic sugar can help to easily generate new language based on a host language. Here assuming we define the DSL for operating drink machine by C macro. And when a customer submits his or her order, the system can form the program in the DSL on the right. After the execution, the user receives the drink. That seems good, but we should not expect too much. If the DSL is defined by syntactic sugars, the general problem is that the first step of executing programs with sugars is desugaring, where all sugars are expanded. Then it's impossible to obtain the intermediate step of the execution on DSL level, which can be useful to know what happens during the execution. Generally speaking, programs in sugar-based DSL is hard to debug without a traditional programmer. There's an existing method named resugaring to solve such problem, first proposed by Justin and Shiram at Brown University. The overall idea is not complex, just to review the sugar in the evaluation sequence by reverse desugaring. Let's see a simple example. Above are two sugar definitions, and for the small program, or one, not true, not false, the traditional desugaring will unfold all sugars and start to execute the program in the core language, just as the right side. So we can only get the final result on the surface level. Alright, the resugaring is like this. In the first step, only the not truth right-hand side is destroyed, right? Then the resugaring will reverse the other sugar expansion. For any steps, we can get the corresponding sequence. In the resugaring setting, they only care about the intermediate sequence with no core structure, so the third step has no resugaring. Well, the resugaring is really a great idea to solve the problem, but I find a possible issue to make it impractical. See the illustration here. Assuming there are m steps of sugar expansion and n steps of core reduction by the traditional execution of term t, there can be OMN steps of reverse expansion in complexity. Is this avoidable? Our answer is yes. By lazy desugaring, the overall execution will be m plus n steps to get the same evaluation sequence as resugaring. Okay, let's see how our lazy desugaring can generate the same sequence. There's a picture which can be scary at first glance, but actually it shows math reduction. If you are familiar with reduction, what I show here is like the lambda calculus full reduction. That is, any subterm in the term can be the place of reduction, called radix. What I care about is the intermediate term with red circle. Maybe you have noticed that they are just as the same resugaring sequence, right? So the initial idea of our method is to find the resugaring sequence in the full reduction graph. But how to make it? Alright, I guess the previous graph is not that helpful. For the same reduction graph, we find some specific terms we want and reorganize them as this one. Start from the top left corner. We have different ways to reduce to the bottom right corner. The way we reorganize it is that for left to right arrow, all of the reductions are the expansion of the sugar. And for the top to down arrow, the reductions are based on reduction rules in the core language. Okay, we can find that all the leftmost term on each line are just the sequences we want. So if we can find a way to execute the DSL program like this, we won't need to reverse expansion anymore. As you can see, the core insight of our work is to expand the sugar at the proper time, and we notice that the proper is lazy for the task. So what is lazy desugaring? Here's the informal definition. Any sugar in the program is not desugared until necessary. Then you can guess the unnecessary expanded sugars are just the same as the reverse desugaring sugar in the resugaring. Intuitively, that makes sense, right? Here's the overall workflow to evaluate programs with sugars. First is calculating context rules and reduction rules for sugars, and then forming the mixed language with mixed evaluation rules. And finally, for any program, we can evaluate it in the mixed language. And if we want, we can specify a filter to remove unnecessary intermediate terms, just as the resugaring. Let's see how to obtain the sugars context rule and reduction rules. The evaluation will be as lazy desugaring. The input of the process are the core language context rules and sugar definition. We have a simple example here that is defining sugar and or with if expression. Okay, you may get the feeling for program headed with and with two subterm. If the first subterm is reducible, then the desugared program won't destroy and structure in one step, right? So intuitively, T1 is the radix. After T1 becomes a value, the and's right-hand side will be reduced. So now it's necessary to desugar the and expression. Okay, that's a pretty simple process. We can get the sugar and or context and reduction rules. And just mix them with the core language. We will be able to have the mixed language to run the program of and or sugars. We have a single function to obtain sugars evaluation rules in the paper, but to avoid introducing so many terms, here we gave two simple examples of the process. Hopefully, it will give you a more straightforward understanding. First, we have the sugar 1 as the input of get rules. Sugar 1 is a sugar with three subterms, where the right-hand side is adding T1 and the sum of T2 and T3. Obviously, the location of T1 is a radix. Then we need a recursive call on a rule with the sugar form, but not the original one. Instead, we replace the meta term with meta value v1, which implies that the location is not reducible in the following rules. Finally, we obtain the list of rules before, where 3 context rules and 1 reduction rules are in it. Alright, please remember the simple sugar for a second, because the next sugar is similar but not the same. Okay, here's the sugar 2, where the sum of T1 and T2 is added by T3. Can you see the difference during the process of get rules? I like to pause for 10 seconds. Okay, you may have find the difference. For this sugar, after T1 and T2 is reducible, the location of T3 cannot be the radix, because the context rule of plus is likely to calculate plus V1, V2 to a value. In such case, sugar 2's right-hand side is destroyed. Therefore, the obtained rules are less. Here are some detailed things for the direction of sugar's rules. For example, if the expansion is non-linear, then the meta variable can appear multi-times on the right-hand side. In such case, the laziness won't work, because there is a time when only part of them is reduced on the right-hand side. So the solution is we can either use a light binding to make them reduce at the same time, or just make the sugar expanded directly when the radix is this meta term. And for multi-sugars, we should calculate their rules one by one, so the context rules should not have cyclic dependency. Actually, the mutual recursive sugar will be ill-formed if we cyclic dependence on the context, just like this. Here's the rest technical part. Okay, our method seems to be reasonable, but what exact property it has? So for formally defining the sugars, the lazy desugaring's correctness, we use 2 properties, emulation and laziness. The overall idea is just like the reduction graph previous. All reductions in our method are either core reductions or sugar expansions. So for the core reduction, we make it corresponds to one step on the fully desugared terms, that is emulation. And for sugar expansion, the fully desugared terms, one step reduction in the core language, will destroy the expanded sugar's structure, that is laziness. Here's the illustration of emulation shown as the case 1 in the figure. And case 2 is part of the laziness, but some other things should hold, because expansion of any sugar in T will follow such cases. Anyway, the full proof is in our paper. We have implemented the method based on PLT radix, since the reduction semantic is easy to use here. Build a small lambda-based core language and test on different syntactic sugars. The tool is available on GitHub. Here I'm showing some interesting case studies. The first one, forced desugaring, is founded when we try using skip combinator as some examples. Since sometimes we won't want to make all sugars be expanded lazily, we can just rewrite it by a combinate lambda calculus, which can be done automatically. After that, the evaluation sequence will be as this. Because the force and sugar has no context rules, it will be reduced to the lambda with 2 parameters, then become if T1, T2 false by the reduction of combinate. It's really interesting, right? Because we skip our lazy by another lazy. Then let's take a look at hygienic sugar. The hygienic macro was proposed by Schemes folks as a distinguished feature from list. What I'm showing here is that lazy desugaring can naturally avoid a kind of hygiene issue named introduce binder hygiene. Just see the meaningless sugar hygienic ad, which introduced the binder X. So for program let X2 hygienic add 1X. If we desugar it directly, there will be a confusion between different X. But by lazy desugaring, we won't need to expand the sugar until necessary. So the binder is introduced without a problem. For more general hygiene, we can extend our method with existing hygienic approach. And now let's see a recursive sugar filter. What I want to show here is that first, the flexibility of grammar-based filter makes the output sequence more straightforward. Second, our approach is more efficient than the resugaring. You can imagine the execution of resugaring here. Alright, the final example is out of the scope in the paper setting because we cannot define the correctness for them. We mentioned previously that some sugars are ill-formed for the traditional desugaring because the expansion will not terminate. But the lazy desugaring can handle some cases when the semantics can be calculated, just like this odd even example. To some content, the lazy desugaring can make the expressiveness of syntactic sugar richer. To make a summary here, we propose a new approach to evaluate programs with sugars. The core insight is to achieve lazy desugaring by semantics of mixed language. We prove two properties to make the evaluation sequence meaningful, and the case study on our tool shows the good efficiency, extensibility, and expressiveness. For the last section, let me describe something about future work. The most related work is to obtain the standalone semantics of DSL. You may remember that we only use the context rules of the core language, but it's possible to make use of reduction rules so that the surface language will not depend on the core language. Just like this and sugar, based on the reduction rules of if, it's possible to obtain one without dependency on if. It is more efficient, but not that simple for some complex cases. The second one is related to the whole picture of the project. It is to automatically generate many tools for DSL based on the core language tools and DSL's definition. So here, the lazy desugaring is the first step, an attempt on evaluator. That's all. Thank you.